Hello everyone. So today we're going to continue on our discussion on 7.2 multiple integration or multiple integrals. So yesterday on the last video, we get to set up this Riemann sum that represents total volume. So now comes the big question. So this Riemann sum is an infinite sum. So based on what you learned in BC calculus, an infinite sum can converge or diverge. So the key concept here is that mathematician Riemann figure out that this infinite sum actually converges to something, and that whatever it converges to actually represent the volume. So now come the part that we want to define a mathematical notation that can capture this concept and allow us to actually evaluate this value. So, and that become what we're going to talk about definition. We're going to define something called multiple integral or Riemann integral. So let's say given a function f that met from Rn to R over a closed region B in Rn, in the domain. The integral, of f over b will form the Riemann sum we set up before, but not just in the, notice that the way we set up our Riemann sum, we actually did not specify what the vector x is. So vector x can actually be anything. Vectors can actually be in any dimension. So in here we can imagine that it's in Rn. So therefore we set up the Riemann sum, limit as n approaches, actually I don't want to use the letter n because I'm already using n right here for the dimension of the function. So I'm going to use a different letter. How about how about k? No, I used k already. How about m? M approaches infinity, summation k from 1 to m, f of vector x sub k, delta, instead of using a sub k, because a stands for area, here I'm going to use the more generic term, the content, which, surprisingly, the content actually uses the letter v, delta v sub k. So in this expression right here, I'm going to go and define that where delta v sub k is the content of a subdivision of B. Which we can imagine this the content of a subdivision of B in whatever dimension that is in, and it could take the form of a rectangle or a rectangular prism, or in a rectangular prism in high dimension that I don't think we have a name for them. So that's what the Riemann sum is. So now come the big question or big definition here. This Riemann sum will convert to something called a Riemann integral. Or we also refer to as a multiple integral, in the form of, so here's the important part, this is how the Riemann integral look like. It will have an integral symbol, no limit, but the regions of integration underneath the integral symbol. The integrand is still kind of like the height of the function, which is f of vector x. And then we have a differential called dv, which is called the content differential. So in here, in this expression, we still have our integral symbol, but in this case, our integral symbol now represent a multiple integral. We don't have limits, but instead we have the regions of integration on the bottom of the integral symbol. This right here is still referred to as the integrand. Integrand, which is basically what the function f is, or in this case, the height. And then what is this thing right here? This thing is still referred to as a differential, but this time this thing is usually referred to as a content differential. Or n-dimensional volume differential. Oops. And this expression is what we refer to as a Riemann integral. Now, Riemann integral, as the name suggests, is also referred to as a multiple integral. So therefore, it can mean many different things. So, give you an example. If function f met from R2 to R, then the Riemann integral would be what we refer to as a double integral. This is referred to as a double integral. And with dA equal to the area differential. And what does this integral give us? Volume. Because this integral is basically what this Riemann sum is going to turn into in R2. And notice that we have delta A sub k, that becomes dA. And what happened if our function f met from R3 to R? When it met from R3 to R, then what we have is called a triple integral. And in this case, our dV is actually referred to as the volume differential. And a question that I often get asked is that does that mean anything different than the content differential or n-dimensional volume differential? No, not really. Neither does dA compared to the content differential. They are kind of the same. The only reason why we probably use dA instead of dV in a function from R2 to R is just make more sense because we are actually talking about area and base area and height. Okay, but in general, you can also put dV in the double integral, which would actually be perfectly okay if you want to do that. So now what would happen if the function just met from R4 or higher to R? Then we no longer give it a quadruple integral or things like that. We just simply collectively call them multiple integral, and we will then use just one single integral symbol to represent them. As a matter of fact, for both double and triple integral, if you want to just draw one integral symbol, you're perfectly okay. The only reason why we actually draw a double integral or triple integral is to emphasize on the fact that these are double and triple integral. And double and triple integral are probably the most common type of integration that we would use. Mainly the reason is, number one, for a double integral, it's great to use that to calculate three-dimensional volume, which is something that we're interested to do. And for function from R3 to R, we actually don't want to calculate four-dimensional volume, but instead we basically using a three-dimensional position and add up something that's a characteristic of a three-dimensional space. One of the common things to do, interesting enough, is that we will use the function f of x, y, z in a function map from R3 to R to represent a density function. And then this integral actually represents some kind of mass. And we'll talk about how that works as our next thing. Okay? So, the important is that for 4 or higher, so maybe I'll write it out anyway. If f map from R3 Rn to R, where n is greater than or equal to 4, then we just have this single notation, and this would actually refer to as just a multiple integral or Riemann integral if you want to. And of course, in this case, our dv become content differential. So the last thing I actually want to talk to you about will be following. So how do we actually use this integral? Well, this integral can be used for many different things. One most common way to use it is to use it to calculate these three things: area, volume, and mass. So let's talk about area. So how do we calculate area? So you now actually have learned two different ways to do that. And you might not realize it, but we actually do know two different ways to do it. Number one, from BC calculus, you can have a function f that maps from R to R, and we can say that the area will equal to integral from A to B f of x dx. So that becomes what we call the net sign area. Between y equal to f of x and the x-axis over the interval from A to B. So that's definitely one way to calculate area, but you now actually learn a second way to calculate area. Area can also be calculated this way. From 7.2, we just learned this. If we have a function f that maps from R2 to R, we can also find the area by doing a double integral over B dA. Meaning we just integrate the differential, the area differential. Then we would technically have the area of the regions B, where B is the enclosed region. Now, here comes the interesting thing. This integral, you might be thinking like, wait, doesn't the double integral like this give volume in R3? Yes, you could. In here, you could interpret it this way, which I'm going to also show you. Ready? Is this: if we interpret that the integrand is a value 1, will represent the height of 1, then this double integral actually represents volume of B with a height 1. But numerically, that will be the same thing as the base area, because if you take the base area multiplied by height 1, you actually get the same exact numerical value, except they represent volume versus area. So that's what we're playing at here. We are treating the height as non-existent, and we just simply integrate the differential dA. Maybe I'll write it out so it make it more sense. So now we can also form volume. So from 7.2, we can also form volume two ways. One way is this, is to have a function f that maps from R2 to R. Oh, actually, you know what? That's probably the reason why. Here, I don't need a function f because I'm not using it at all. Okay, but now what if I have a function f that maps from R to R? Then we can say the volume would equal to integral, double integral over B, f of vector x dA. So that represents the net sign volume, because depending on whether f is positive or negative, net sign volume between z equal to f of vector x and the xy plane over the regions B. Now we could also do this. We can also calculate the volume could also equal to a triple integral B dV. That also equal to a volume, but this equal to the volume of B. Now maybe I draw a picture to help you see the difference between the two. Okay, and I'll probably draw a picture over here too so you can see it. So from BC calculus, this is the volume, this is the area that we're looking for. Okay, that's from BC calculus. From 7.2 with what we just learned, we can also draw a area. So here would be different. The picture would be this. And once again, I'm just drawing in the first quadrant for simplicity reason. And this integral will find the area right here. Different. So same thing happened here. In the first scenario right here, we will be drawing this. So that's the volume that we're looking for in this case. Let's see if we can try to make it look nicer. Which is kind of like a rectangular prism shape. But for this way to find the volume using a triple integral, I can actually form something like this. Where B is a three-dimensional volume object, and I can find the volume of that using this triple integral, provided I can, kind of define what B is in some way. So now comes the big question. The next question will be, what if I want to calculate mass? How do I do that? Well, guess what? Our triple integral can actually do that. So let's say we're given a closed regions in R3. So in my mind, I always kind of visualize this closed region like the inside of a sphere. Let's say we're given a density function. Which we call mu of vector x, and since the density function have to be greater than 0. So now imagine that I have some kind of shape. So I'm going to just try to draw and maybe the front can be like this too. Okay, so some kind of solids which we call B. And let's say in this case we would say that the density inside this solid is different everywhere and is defined by the function mu. Okay, so that thing defines what the density inside is. So now how do we actually calculate this mass of this thing? So, well, let's take a minute to think. You hopefully remember learning in physics, if you have a density, you can calculate the mass by saying multiply by the volume. So a general concept is that mass is equal to density multiplied by volume. But of course, that's assuming that the density is constant. Then you can just multiply by the volume to come up with the mass. But what if the density is not constant? Like in this case, the function is defined by function mu. Well, then what we're going to do is the following. We're going to do the same thing that we did before. What I'm going to do is I'm going to pick a value inside this solid, and we'll call that vector x sub k. And we're going to draw myself a little cube. And I'm going to say that this cube have a volume where we call the volume to be delta V sub k. And what I'm going to assume is that inside this volume, the density is exactly the same as defined by vector x sub k. Now, I know it's not true. The density is probably different inside this cube too, but let's assume that it is the same. So in this case, then at x sub k, the mass of the small regions defined by the k value, the mass of the k regions, would be equal to, or approximately equal to, because remember the density is not the same, but we're going to assume the density is the same and just use this one corner to define the density for the entire cube, and then multiply that by the volume. So that would kind of give me the mass of this one little cube. And what we're going to do is, well, how about we add up a whole bunch of them? We can now try to find the total mass, which should be approximately equal to the summation of all these together. All these mass of these regions together. And now what if I try to make each one smaller and use more of them to actually estimate the mass? Well, then eventually this total mass can be calculated to an infinite accuracy if we allow this process to go on forever. And guess what we have right here? This is a Riemann sum. And this Riemann sum doesn't represent a fourth dimensional volume, even though you can picture the function mu of vector x is a function map from R3 to R1. So you could interpret it as a three-dimensional surface in R4, but in this case the output is actually not an extra dimension, but rather is a property of the solid, which is called the density. So therefore it actually doesn't increase the dimension, but it still results in a triple integral because the function mu is in from R3 to R1. So therefore we can now say that the mass of B is basically given by a triple integral over B mu of vector x dv. So therefore there are quite a few different integral here that you need to get familiar with and know what to use. Number one, this is the mass integral. We can have a volume integral this way or this way. Notice that they generate different types of volume. One of them generate volume that has to kind of look like a cylinder shape or like a column shape, while the other one can be a volume of any shape that we like, just shape of B. And then similarly, we can have an area integral, which allows us to form any area of any regions B, or it can form the area of a kind of like a rectangle with a curved top type thing. Okay. All right. Unfortunately, that's the end for 7.2. So now what we're going to do, now that we know how to set up the integral, at least represent it mathematically, the next thing we want to learn would be how to actually evaluate one of these. If I do have the function f or the function mu, can we use it to find the mass? Or if we have the function f, can I use a double integral to find the volume? How we actually calculate the volume? That would be talked about in 7.1. All right, that would be it for today, and I'll talk to you in the next video. Okay, bye-bye.